In section 5.2, we're going to continue our talk about integrals. And we learned in 5.1 that all an integral represents is the area between a curve and the x-axis. And in this section, we're going to talk about how to use what's called right and left Riemann sums to approximate that area. I wanted to start with a few motion problems, just so you can see the importance that integrals are going to play in our discussion with motion. In this first question, it says you drive a constant 70 miles per hour for 4 hours. And how many miles have you gone? This is just a simple application of that d equals rt formula, distance equals rate times time. When you have a constant rate of 70, you multiply it times your time. And you can see when I do this, even my units turn out right. I cross out my hours, and 70 times 4 is going to give me a total distance of 280 miles. I wanted to present this to you in a time versus velocity graph, just so you can see that we are really actually just calculating an integral when we're doing d equals rt. Here is my constant rate, my constant velocity of 70 miles per hour. Over 4 hours means I'm going to block this off from 0, which is just the y-axis, to 4. It creates this rectangular shape, and finding the area of the rectangular shape, it is 4 units wide, and it is 70 units tall. So finding the area of that rectangle, I'm really just finding that distance. This idea is going to play an important part in some upcoming sections. The next one says we're going to assume now a constant acceleration of 5 miles per hour. So for each hour, my velocity is going to increase 5 miles per hour. Starting at 0, at the first hour, I'm going to increase 5 miles per hour, and that's why you see that velocity is now at 5. In the second hour, I'm going to go up another 5 miles per hour, so now I'm at 10, and so on. And it creates this linear graph. Because this is not a constant velocity, it's a constant acceleration, d equals rt actually gets me nowhere as far as finding my total distance traveled. But since we've just connected the distance traveled to the area between the graph, the velocity graph, and the x-axis, we'll be able to find the distance traveled under the scenario under the first 4 hours. I just block this off between 0, and I have a natural barrier there, and 4, and it's the area underneath the graph between the x-axis, which is represented by this triangle. Find the area of this triangle, and we found our distance. The base of my triangle is a 4, and the height of my triangle is this 20, and that leads me to a distance of 40 miles. There's a second part to this question where I want to know what that distance traveled is just on the interval from 1 to 4. That means I would block it off here, and the region I would be looking at is this one. Doing this turns my triangle into a trapezoid, so now I'm finding the area of a trapezoid. Trapezoids are very important to your future, so even though you can just back out this little triangle right here and find the answer to this particular question this way, working with trapezoids is really important. The height of my trapezoid is the distance between the two parallel sides, which in this case would be a 3. I know that this base right here is 20. The second base over here, the smaller one, is a 5. And plugging that into my trapezoid formula gives me 1/2 times the height times the sum of the bases. And it tells me that that area is a 37.5. But actually, if you were going on a 4-hour trip, it would probably look something like this with your velocity. It would have a variable speed. So you might start out going 60 miles per hour, and then no traffic, smooth sailing, and then you're going to have highs and lows. You might hit traffic. There might be a cop. There might be an accident. You don't know. But it looks more variable like this one. So the question becomes, how are you going to find the total distance traveled when your speed varies like this one? What we know is it's represented by the area underneath the curve. So I could block this off from 0 to 5 for this 5-hour trip. And if I could find the area of this shaded region, then I have my distance traveled. My problem is I don't have a geometric formula for this shape. So our idea is to divvy it out into rectangles. So I could split this region up into various rectangles, and I could find the area of each one of these rectangles, and you can see that that would give me an approximation for the area that I'm looking for. This area of this rectangle would be this first hour times whatever my speed was at the end of that first hour. Then my 1 hour here, whatever my speed was at the end of that second hour, and so on. And you could see it would give me an approximation. There are some pieces I'm missing that aren't included in that area, and then there's some pieces that are included in my area that shouldn't be, but it is just an approximation, and you can see it would approximate that distance. But instead of just splitting it up into 5 rectangles, how about if I do 10 rectangles instead? And again, I could easily find the area of each one of these rectangles, add them all together, and it would be an even better approximation. But why stop at 10? We could split this into 20 rectangles. And you can see by doing this, I get an even better approximation. We don't really want to do that because that entails a lot of just tedious work, but it could be done. What I want you to see, though, is that the more rectangles that I use, as the number of rectangles increases, my accuracy of my approximation increases as well. So the smaller I make these sub-intervals, these rectangles, the closer to that actual area, the closer to that actual distance that I traveled will be achieved. We will eventually learn how to find the exact area underneath the curve. That's what an integral is all about. But these first 2 sections, this one and the next one, we're going to learn some approximating methods. In this one, we're going to focus on what's called the left Riemann sum and a right Riemann sum. And all a Riemann sum is a systematic way of drawing these rectangles. Whenever you have a left Riemann sum, sometimes called LRAM for short, stands for left rectangular approximation method. What you're looking for when you're drawing these rectangles underneath the curve, so my graph of f of x is this parabola shape, and what I'm looking for is for the left corners of these rectangles to be touching on that f of x graph. What's important to notice about each of these rectangles is that that left corner is sitting on the f of x graph. When I want the height of the rectangle, you can see that the base is just that x interval, but when I want the height of that rectangle, I'm going to plug in that x value that's sitting on the left side of each particular rectangle. So for the second rectangle, I know that the width is whatever this is, that's the base, and the height is going to be given by whatever I get when I plug this x value in. So for this third rectangle, I know that its base is whatever this x interval is, and the height is going to be obtained by plugging this x value into my f of x, and whatever that y value is tells me what the height of that rectangle is. And then I have one more, and same thing. If I want to know what the base of the rectangle is, I just look at that x interval, and the height is obtained by taking that x value that's on the left side of the rectangle, plugging that into my f of x, and whatever value is given tells me what the height of that rectangle is. That's what all of this down here says. Don't worry about memorizing a formula, just know what you're doing graphically. A right Riemann sum is everything a left Riemann sum is, but on the right side, called RAM for right rectangular approximation method. And what you'll see is that the right corners of each of these individual rectangles is sitting on the graph of f of x. So when you go to find what the height of the rectangle is to find its area, for this first one, you'd be plugging in that x value that's on the right side to obtain the y value, and it's the y value that tells you what the height of the rectangle is. For this second rectangle, I know that the base is whatever that x interval is, and the height will be given by the y value when I plug that x in, and so on. So again, don't worry about memorizing a formula, just know how to do it graphically. The height of the rectangle is given on the right side of it. Before we jump to some examples, one more thing that's important to know is your approximation an over or under approximation of the actual area underneath the curve? And what's going to determine that is the increasing or decreasing nature of the graph. When you have an increasing graph, you can see that these left approximating rectangles, and what makes them left is the fact that the left corner of each one is sitting on the curve. You can see that I'm missing chunks of area, meaning this is an underestimation. But when I do a right Riemann sum on that same increasing graph, and again, a right Riemann sum means the right corner of each of these individual rectangles sitting on that blue graph, you can see that I'm including areas that are not underneath the graph. Therefore, this is going to be an overestimation. If I switch the graph to now be decreasing, just the opposite happens. My left Riemann sum, again, the left corners of these rectangles are sitting on the graph, creates an overage because I'm including these chunks in my answer that are not technically underneath the graph, so that's an overestimation. A right Riemann sum on that same decreasing graph, because I am missing chunks of area, I'm missing these, it will be an under approximation. When you're asked over or under approximation, you're going to refer to the increasing or the decreasing nature of the graph. It has nothing to do with the concavity. Let's go ahead and take a look at a couple of examples. This first one wants me to use a left Riemann sum to approximate the area between f of x and the x-axis on the interval from 1 to 3. First, realize that what we're doing is we're calculating an integral. We will learn exact methods for doing that, but right now it's about these Riemann sums. So my interval goes from 1 to 3, so I'm first going to block off my graph from 1 to 3. Wants me to use 4 subintervals of equal length. To find what each subinterval is, if you can't just figure it out, you might look at this and say, oh, I can tell how I'm going to divide this out. But if you have trouble, you can always just take your limits, subtract them. So 3 minus 1 is my 3 minus 1. Divide by however many subintervals you have, which is 4. And I get that each subinterval will be 1/2 unit in length. So I'm going to draw the sides of my rectangle every 1/2 unit. So starting at the 1, so I'm going to draw up at the 1.5, the 2, the 2.5, and the 3. With a left Riemann sum, what that means is I'm going to draw the tops of the rectangles on the left side. So I'm going to travel up the left side of this first rectangle. When I hit the graph, that's where I draw the top of the rectangle. I do the same for the second one. I travel up the side. Where I hit the graph, I cut across and I draw rectangle number 2. I do the same for the third. I go up at the 2. Where I hit the graph is where I draw the top of the rectangle. And then my fourth one would be looking like this. What's important to note about each one of these is the left corner of each one of these is sitting on the graph of f of x. Now my job is just to find the area of each one of these rectangles. I'm going to take them one at a time. So this first one is 1/2 unit wide, and its height goes up to, I can read from my graph that it's a 6, but don't trust your graph. The best way to do this is to take that value of 1 and plug it into your f of x function. So f of 1 is going to tell me what that y value is there, which represents the height of that rectangle. When I get to rectangle number 2, which is this one, again, I can see its x values go from 1.5 to 2, so it's 1/2 unit along the base. The height is obtained on the left side, and on the left side, my x value right here is a 1.5. If I plug a 1.5 into f of x, it's going to tell me what that y value is, so f of 1.5 is the height. Rectangle number 3 is right here. 1/2 unit wide. Its height is obtained by plugging the 2 into f of x, so f of 2. And the height of my last rectangle is when x is 2.5 will give me the height, so 1/2 times f of 2.5. Because each one of my rectangles had a uniform base of 1/2, I just went ahead and factored that out. I already calculated the f of 1 to be 6. The f of 1.5 is the 6.75, the f of 2 is the 7, and the f of 2.5 is the 6.75. Totally use a calculator to do that. When you do all these calculations, you end up with an answer of 13.25. And that is my area approximated using a left Riemann sum. Another popular kind of question is to do these Riemann sums using a table of values. In this question, I'm given f of x as a continuous decreasing function. I just have select values in the table. It's asking me to use a right Riemann sum to approximate the area between f of x and the x-axis on the interval 0 to 7. That encompasses the whole table. And it says to use 3 subintervals indicated by the data. What this means to me is they don't have to be equal length. I'm going to go based on however it's broken up in the table. So from 0 to 1 is one interval, from 1 to 5, and then from 5 to 7. I did a little sketch of these values. I really don't know what f of x looks like because I only have 4 points on it. But it'll help you see how we're using this right Riemann sum until you get comfortable just using the table without a graph. The way that these x values are broken up in the table tells me how I'm going to break up my rectangles. So from 0 to 1, from 1 to 5, and from 5 to 7. So my 3 subintervals goes from 0 to 1, from 1 to 5, and then from 5 to 7. The height of each one is given on the right side. So for this first rectangle right here, I'm going to draw the top of the rectangle by going up the right side till I hit that point on the graph, and then I'm going to cut over. So my first rectangle is going to look like this. The second rectangle, I go up the right side till I hit that point on the graph, and then I draw my rectangle there. And my third one, go up the right side till I hit that point, and then I come over. So the 3 rectangles whose areas I need to find are right here. Again, don't lose sight that all we're doing is calculating an integral. We're just doing an approximation. I'm finding the area of these 4 rectangles. The first one is 1 unit wide because my x's go from 0 to 1. So it's a 1 by whatever the y value is on the right side, which is obtained by f of 1, which is the 9. So this first rectangle is a 1 by 9. Rectangle number 2 goes from a 1 to a 5, so it's 4 units wide. Its height is given by whatever the y value is when x is 5, and f of 5 is 2, so it's a 4 by 2. Rectangle number 3 goes from 5 to 7 on the x, so it's 2 units wide, and the y value is given by whatever the y value is at 7, which is a 1, so it's a 2 by 1. I want you to see how we can come up with these areas without doing the graph. If you look at this first interval that goes from 0 to 1, just looking at this difference in that subinterval from 0 to 1 gives me this 1 right here. And if you just pick the number that's on the right side of that interval, which is a 9, it gives me this 9. And then we move on to interval number 2, and that extends from a 1 to a 5. The base of my rectangle is just whatever the length of that interval is. So from 1 to 5, that length is a 4, and that's this 4 here. And the height of my rectangle, you can just look at whatever height is given by the right side value on that interval, which is the 2, and that's this 2. My last interval goes from a 5 to a 7. The interval length from 5 to 7 is 2, and that's this 2. And the height of that rectangle is given by the y value on the right side, which is the 1, and that's the 1. Doing these calculations gives me a 9 plus 8 plus 2. It tells me that approximate area is a 19. The important part of this problem and the step that is mandatory is this one right here. Make sure that when you show the work on a right Riemann sum or left Riemann sum, that you show me the products and the sums. What needs to be shown is a product and the sums that are involved in this Riemann sum. And actually what you see for my AP exam tip number 2 is that the calculations, this part, is actually optional. My last question wants to know if my answer of 19 is an over or an under approximation of the actual area. what I'm told about f of x is that it's decreasing. I would need to be told that f of x is decreasing. I could not draw that assumption just looking at these decreasing values. I need to be told that this graph is decreasing. And what we said above is if you have a decreasing graph, then a right Riemann sum would result in an under approximation. So because I am told f of x is decreasing, I know that my right Riemann sum is an under approximation, and this is pretty much all you need to say right here.